Now let us do some numericals for the strain energy in order to understand uh, the concept of applying strain energy methods that we have learned in our theory a bit more better. Okay, so let's make it a note here. Okay, determine the bending strain energy in the beam and the total strain energy in each of the 2 points. ठीक है, यहाँ पे हमारे पास बीम है. ऑल मेंबर्स आर मेड अप ऑफ एल्यूमिनियम and have a square cross section of 50 by 50 mm. Okay, 50 millimeter square. Assume the points only supports an axial load. They saying that only that the post, this two posts यहाँ पे भी है. Assume that the post only supports an axial loads. By post is meaning these two columns, and this is the beam. Okay, the beam has a uniform loading of 8 kN per meter, and this is basically uh, the height of the post or the columns. Okay, so first you calculate area, which is 50 millimeter square is 2.5 minus 3 meters square. The moment of inertia, since they are of square cross section, so we will apply 1 by 12 B4, not BDQ, because it's square. So we get this 0.5203 10 to the minus 6 meter 4. Now you apply the bending strain energy. Now when we apply the bending strain energy, we get 0 to L m square dx over 2 ei. Okay, so what we do is basically we are interested in this m square. And in order for this m square, what we need, we can do two things. First we can do is basically we can he's asking for us that bending strain energy in the beam and the axial strain energy in the two posts. Okay, so the axial strain energy we can calculate very easily. U internal energy equals to 0 to L n square dx over 2 EA. E is given for the aluminium. A is 15 to 50 millimeter, and 0 to L, it comes out to be equals to this L will be basically 1.5 meter, 0 to 1.5 meter, n square, and you integrate it, you will get basically the only thing that is important is that since this will be 24 kilonewton, so the two basically at the end conditions of this beam will be 12 kilonewton. So the axial load will be n square will be 12 square, 12 into 10 to 3 ka whole square dx. When you apply 0 to L, it becomes basically x, and x equals to L, so it comes out to be equals to 1.5. 2 E is given 17.6, and A is basically 2.5 into 10 to the minus 3. Okay, if I am not 2.5 into 10 to the minus 3 meters square. Okay, so you apply this and you get the internal strain energy equal to 0.617 joules. Okay, so and then basically in order to calculate the bending strain energy for the beam, which is going to, we'll apply this equation 0 to L m square dx over 2 ei, and 1 upon 2i is taken out, and we basically will cut the beam at any point x. We have cut the beam. This was basically loading 24 kilonewton. So what we are doing is basically, and it will be applied at the mid. It will be applied at the so it comes out to be equals to 12 into 3x minus 4 into 2x square. Okay, this is the bending moment. and they calculated as 1.78 kilojoules. Okay, so we can do it over here. If I have here the same numerical, do it on by hand. This was 24 kilonewton. These are the two reactions when we calculated, because the loading was there of 8. I think the loading was how much? 8 kilonewton per meter acting at distance of 3 meter. It comes out to be equals to, okay, if we take a uh, resultant loading effect as 24 kilonewton, okay, at the mid. So basically for this whole loading, if we cut this beam at any point x, this is 8 kilometer, this is x, this is 12 kilometer, this is the shear force V, this is the bending moment M. So what we will get is the moment, the resistance bending moment will be m not equal to 0, it will be minus 12x plus 8x into x by 2 plus m equals to 0. So from here the internal bending moment comes out to be equals to 12x minus 4x square. Now this 12x minus 4x square is basically being it will be the internal bending strain energy 0 to L m square dx over 2 EI. This function is being plotted over here, 1 upon 2 EI 0 to 3 12x minus 4x square the whole square dx. So this is, if you look at a minus b the whole square, so you basically expand it, and 1 upon 2 EI 0 to 3 you expand it, a minus b the whole square. This formula comes out to be simple. And why you take 0 to 3 over here? Because if you look at it, this length of the beam is from here to here, 0 to 3, okay, from this midpoint to this midpoint, okay, not from this corner to this corner. Don't get confused into that. So once you do that, you get basically the bending strain energy as 1.782 kilojoules, okay, and internal strain energy, exit strain energy is basically from n square dx over 2e, because we have calculated it. Another numerical. And determine the deflection at point B on the beam. I is equals to 18 10 to the power 6 millimeter for E is 200 gigapascal, and this distance is 3 meters from A to B, and from B to C is 5 meter, and the load at point B is 20 kilonewton. Okay, so you take out the reactions, you basically you get RA equals to 12.5 kilonewton and RC equals to 7.5 kilonewton. Okay, and now what you do is, because the distances of the point load 20 kilonewton is not in the midpoint, so we will make a one cut from A to B, and we will try to see what is the internal resistance bending moment, and another cut from B to C. Okay, so when we apply the cut, we have got this RA as 12.5 kilonewton, and we basically cutted a section point x1, so we get V, and this is the internal bending moment m1. So apply sigma m not equal to 0, we get m1 equals to 12.5 x1 10 to the power 3 Newton meter. Now the other one we make it from B to C, okay, and we get this is m2, this is v0, this is 7.5 kilonewton, and when you apply sigma m naught, you get equals to 7.5 into 10 to the power 3 x2 Newton meter. Now what you do is you apply the formula for the internal bending strain energy equal to 0, the 1 upon 2 EI 0 to L m square dx over 2 EI. So if you apply basically from the first one, when we apply this formula, it will be from 0 to 3, and the other will be from 0 to 5. So you apply this function 12.53, m1 was x1 square dx1 plus 7.5 into the second one, 7.5 into 1 10 to the power 3 x2 the whole square, because it was m square dx2, and we can take it out to 1 upon 2 EI as a common, 0 to 3 to 0 to 5. You now integrate, and once you integrate it, you basically get the internal bending strain energy as 1.87512 over EI into 10 to the power 9. Very simple. Now you apply the law of conservation of energy, and you know that basically external strain energy is equals to internal strain energy. So you know what is the external strain energy is basically when this vertical force is being applied, it will be half P delta. So since this point is delta B, so it will be half P delta B. So half P is 20 kilonewton and delta B we need to calculate. So external strain energy comes out to be equals to 10 to the power 4 delta B. Internal strain energy is this. From where we got this internal strain energy? We got it from, this was our internal strain energy. 1.87512 over EI into 10 to the power 9. This was our internal strain energy. So these two energies when we equate, we get deflection at 10 to the power 4 delta B equals to the internal strain energy, and we get deflection at B as 11.72 millimeters. Now this numerical located, this is a beam. At point B you have got a roller support, at point C you have got a triangular support. Now determine the slope at point A of the beam. EI is constant. This is the point A, you need to find the slope. Okay, from A to B you have length is A, from B to C is length is A, and C from this point C to this point the length is A. This is a roller support, this is a pin support. Okay, and the external load is in the form of this couple moment M naught. You need to calculate. Now how we will deal it? We will say distance from here to here is x1, and from the B to C the distance is x2, and the other distance will be treated as this distance is x1, this is x2, and the other distance, basically we cut from the first distance as x1, and from the other distance, if you look at it, this point, it is this end point is basically x2, and if we cut it from here to this point, it will be basically a plus x3. Okay, so these are the different, this section is this one, this section from x2 is basically this section. Okay, and this midsection will be treated as a plus x3. Okay, so this is how we do it. Okay, so first of all is basically this is a ruler and a pin. We need to find the reactions, and you apply sigma fy, you get rb equals to rc. You apply summation of moments at c equal to 0. So when you apply summation of moments c at equal to 0, you get rb is equals to m naught upon a, and you get rc is equals to m naught upon a. You apply rb rc आपके पास आ गया, and you know rb is also equals to rc. Now very simple, from here when we at this point when we make a cut, we make a cut over here, we have this couple moment and this m, so this m will be equals to minus m naught. Okay, and when at this point if we make a cut, this will be, there will be another this moment, but this moment will have no other perpendicular distance acting over here, and there is no force also acting, so we will say this moment equals to 0. And what about this one, the third one, which is cut over here, and distance from here if calculated is a plus x3. This is the point where you weight the bending moment internal into m, and you know what was our what was this? R, you know, RC was m naught upon a. Okay, so basically when you make the moment, it will be basically that moment will come out to be equals to this interest m, and this will be basically clockwise, so it will be minus m naught of a times x3. Okay, so m comes out to be equals to, both are clockwise, so m equals to minus m naught a times x3. So now you apply this moment and these moments, internal moments in this internal bending strain energy equation, m square dx upon 2i, and remember each distance is of a, these all distances are equal at a. So 1 upon 2 a 0 to a, this one minus m naught square dx1. What about the second one? That's actually, which is the third one actually, 0 the whole square dx2, and this mid and the last one, it will be 0 to a minus m naught upon a x3 the whole square dx3. Okay, and you basically close down. Now basically what you do is simple integration. This function will automatically get 0, and this you add together, you will get internal strain energy equals to 2 m naught square a upon 3I. Okay, but since in the theory I've told you what since this is an external couple movement, so the work done by this external movement will be half half m naught theta a. Okay, why theta a? Because this m naught is acting at this point, so it will, the slope will be considered at this point where the couple moment is acting. So half m theta will be equals to half m naught theta a. So external energy, strain energy equals to internal strain energy. So external strain energy is half m naught theta a. Internal strain energy is 2 by 3 m naught square a upon ei. From here you can get the slope of this beam comes out to be equals to 4 by 3 m naught a upon ei. So this is the slope of the beam. Okay. Now we go to another theorem, which is the Castigliano's first theorem for deflection. So Castigliano's first theorem states that if the total strain energy of a body, a framework, is expressed in terms of external loads and is partially differentiated with respect to one of the loads, the result is a deflection of the point of application of that load and in the direction of that load. So if U is the total strain energy, then deflection will be W of the direction of load W will be tau U over W. Okay. So in mathematical terms, what does this means? That if you strain energy and you want to find the deflection at any point, so for that function you basically differentiate that strain energy function with respect to the force which is acting at a specific point at location A. Okay, so dava u and dava p, which means this p is the force which is acting at point A, will give you the deflection A. It can be another point B, so it will come down to be dava u or dava pb. It will give you deflection at point B. It will be the B. So the partial differential of the strain energy U with respect to PA gives the deflection and in the direction of PA. Okay, so deflection will be under and in the direction of PA. So dava U or dava PB equals to B, and dava U or dava PC equals to C. So in most beam, as we already discussed, in that the strain energy, whenever we consider beam strain energy, we will only consider the bending deflections, and we will not consider strain energy for the torsion because it is very small, and we will also not consider the end loads, which means where the supports are there will be almost no deflection. Okay, so this is what he's trying to say us. So now you know what is the bending strain energy. Bending strain energy equal to U equals to interior m square ds over 2ei. But if you differentiate this U with respect to any force P, dava U, dava P, we can write it as dava U or dava M into dava M or dava P, which is still the same as if you look at dava U by dava P. So now this function dava U is U differentiated with dava by dava M and equals to dava or dava M will give you this thing, the M square upon 2ei ds into dava or dava M. So it comes out to be equals to, after differentiation, 2m over 2ei ds into dava m over dava p into dava m over dava p. So here if you 2 gets cancelled out, so we will be getting dava u by dava p is nothing but it's a deflection equals to m upon ei dava m over dava p times ds, which is usual form of the Castigliano's first theorem. Okay, I told mathematically when you integrate it within the differentiate a function within the integrand, it is a mathematical technique called the Leibniz technique. I have told you before also when we are doing SIB, the statically independent beams. And just to let you know, this is the deflection, but we have another technique in Castigliano's theorem. If we want to remember, very important, if you want to find the slope uh, of a beam, then we will use this equation, like theta will be equals to dava u over dava, instead of p will be dava m naught. M naught will be the couple moment, equals to m upon ei dava m over dava m naught times of ds. So this function can be changed as theta equals to dava u or dava m naught equals to m upon ei dava m over dava m naught times of ds. So just remember this. With Castigliano's theorem you can calculate the deflection, and from the Castigliano's first theorem you can also calculate the slope. Now, using Castigliano's first theorem, obtain the expression for a deflection under the single concentrated load applying to a simply supported beam. This is the load, and these are the two supports, WV upon L, WA upon L, AB, very simple numerical. Since it's not placed in the center, we will cut it at two different positions. One I will cut it at x1, the other will cut it at x2. When we cut it at x1, we get the moment as WBL upon x1. When we cut this and other position at x2, we get moment as WL upon x2. So now this m is to be differentiated with w, because the load is yw, because the load is w. So dava m on dava w equals to v upon L x1, and what we'll do here, again the load is w, so it will dava m on dava w a upon L x2. So you've got m, you've got dava m over dava w, you've got m, and you've got dava w for x2, and this is for x1. Now you will apply same these two partial moment and differentiations to be applied in this function. Deflection a to b m upon e dava m over dava w ds. So we'll write integral a to c m upon e dava m over dava w ds plus c to b m upon e dava m over dava w times of ds. So when you apply, you will get 1 upon e 0 to a wbl upon x1 b upon l x1 dx1 plus 1 upon ei 0 to b. Okay, once it was 0 to a, now 0 to b wa upon l x2 a upon l x2 dx2. Now simply basically wb square upon l square ei can be taken out, and we will left with integral, and x1 becomes x1 square dx1 plus same with this x2 square dx2. Simple integration you perform, you will be getting wb square upon 3l square ei x1 cube 0 to a plus wa square 3l square ei x square cube 0 to b. Okay, so once when you apply and you integrate it, you apply this condition, limit a, it becomes a cube, and here it becomes b cube. Okay, now what you can do further is basically w so this was basically w b square upon 3l square ei, and it's again w a square b cube over 3l square ei. So basically this w a square b square over 3l square ei is taken out, and from here and here terms we take it out a plus b, and if you look at it, this a and plus b, if you look at it, is basically nothing but it is the length of the beam. A plus b is length, so the deflection comes out to be equals to what comes w a square b square over 3 lei is the which we have calculated from the Castigliano's first theorem. Okay, this is how basically apply. And with this, basically, we have done the numericals for how to get the deflection from the strain energy method techniques. And not only that, but we also did it how to get slopes. And then we applied Castigliano's theorems, and from the Castigliano's theorem we can get deflections, and we can also get the slopes as per our requirements.